All right, exciting stuff today. We are going to learn all of our properties of logarithms. And what are logarithms again? Just to stress it, those are used to solve for unknown exponents. When you are trying to solve for a variable exponent, like what power of 5 gives me 8, you need to use logarithms. Okay, so last time we did talk about a log with base 10 was referred to as a common log. So if I wrote log base 10 of y, you could write it without the base, and the base was assumed to be 10. That was called the common logarithm. Today we're going to learn about something called the natural logarithm. And it has to do with a new number, a new irrational number, which means as a decimal it goes on and on forever and never repeats, very similar to pi. This number is called the natural number, aka Euler's number, and its decimal approximate value, we go to 3 decimal places. It's 2.718, about 2.718. And this does have to do with natural growth rates and things that occur in nature. It comes up a lot. Here's a really quick, cool description of E. If you were to graph the parent function of our rationals, like we did in the previous chapter, 1 over x, the area under the right-hand side of this curve between 0 and some value that gives you exactly 1 square unit of area, you would need to stop at an x value of e. So you'll learn more about this in, say, calculus, but I thought that was kind of a cool little introduction. Okay, now a logarithm that uses e as its base, and this does come up quite a bit, is called the natural log. So log with base e, and again this is a number, right? The number e, just like the number pi, is also used, so frequency, it's given its own button on most calculators, and instead of writing log base e, it has a shortened version, ln. So this is the natural log, ln, or log natural. I don't know, maybe it's French, but it's shortened as ln of x. That just means a log with base e. Okay, we will see that a lot, so make sure you know that one. Okay, so here are our 3 properties we need to learn today. For positive values of u and v, okay, so the inside values, part of our definition of logarithms is that the inside values have to remain positive. So I will stress that here, that when I have log base b of y equals x, okay, y has to be a value greater than 0, and the base has to be greater than 0 and can't equal 1. So these are some restrictions on logarithms in general. Okay, the inside value has to stay positive or the logarithm is undefined, and our base has to be a positive value not equal to 1. Okay, so a little bit of restriction. So for positive values inside of our logarithm, u and v, and positive value of b where our base does not equal 1. So that actually just comes from our normal logarithm. We have what is known as the product rule. If you have 2 values being multiplied inside of a logarithm, you can expand them out as 2 separate logarithms being added together. And a good way to think of this is repeated addition means multiplication, right? So multiplication has to do with adding 2 logs here. And this goes backwards and forwards. So if you have 2 logs being added, I can condense that into 1 log, or I can expand it into 2 logs being added. Okay, so likewise, if that's true for multiplication, usually it's true for division. And if multiplication, we are adding 2 logarithms, division means we are subtracting. That's right, you guessed it. In the order of the top minus the logarithm of the value in the bottom. So log base b of u minus log base b of v. So if we have 2 logarithms being subtracted, we can write it as a single logarithm with division of their 2 values. Or if I have a logarithm with a fraction, I can expand that out into 2 logs with subtraction. And sometimes we want to do both. So it's good to know we can go backwards and forwards. This last one, little less intuitive, but it's called the power rule. And this actually says if you have an exponent acting on everything inside of your logarithm, you can actually bring that exponent out in front as a multiplier, like n times log base b of u. So this n actually just comes out and becomes a multiplier times our logarithm there. Okay, but you can only pull that out if n is acting on everything inside of your logarithm. If, for instance, you had something like this, 5x squared, where that exponent of 2 is only acting on x and not the 5, you cannot take that exponent out as is. You'd have to do some more manipulation. Okay, we're going to do some expanding and condensing here. And as kind of a rule, we want to follow when you're condensing, we are simplifying. Okay, to give you an idea what I'm talking about, I'll go ahead and load up the first question, which is to use our above rules and condense this expression into a single logarithm. Okay, when we're condensing, we're really simplifying, right? We're taking things like this and making them into one single logarithm. So we want to kind of follow order of operations, right? So think of PEMDAS, right, or order of operations. Parentheses, of course, exponents. And our rule that has to do with exponents is the power rule. Multiplication, that's the product rule. Division is the quotient rule. Okay, I know these are technically, you can do them at either one at the same time from left to right. That's kind of true. But I can tell you, you're really better off doing the multiplication and then the division, or the product and then the quotient in the end. Okay, so let's try some of these. To condense this down, the first thing I want to do is look to see if I can use the power rule to condense. So I want to go that direction if I can. So I want to look for, do I have any multipliers on the outside? And in fact, we do. We have a 2 and a 3. And what we can do using our power rules, bring those in as exponents. So we now have log of x squared plus log of y minus log of z to the third. Okay, now you could have maybe brought that in as z to the negative third power, but I tend to want to stay away from negative exponents if I can. It's not technically wrong, but this is my preferred method. Okay, next we're going to do any product rule. So the product rule says if I have any logs being added, we can write them as a single log and multiply the values inside of them. So for instance, these two logs right here being added, we can write them as a single logarithm and multiply the two values inside. So x squared times y minus log of z cubed. Okay, lastly, we would look for a quotient rule, which says if I have any logs being subtracted, we can write them as a single logarithm with division of their values. So log of x squared y over z cubed. X squared y over z cubed, all inside my one logarithm. And there's my answer. This is the condensed down answer. Now, I should have specified here that this log, of course, was log base 10, the common log all the way along. And you do want to keep that base, of course, as you continue to condense. But with base 10, you don't need to write the base each time. All right, I just brought our rules and stuff along with us here at the top. Let's do a couple more condensing. So you can try number 2 out. This would be a good time to pause and see if you can repeat those rules, and then we'll go over 3 together. So go ahead and pause now. Try number 2. All right, there's our final answer. You should have gotten to log of 16. Log of 16. So you can check kind of the steps here. I tried to kind of underline the things as I did them. Okay, let's move on to number 3. Here we have a natural log. I can see we do have parentheses. So think of order of operations. We always want to simplify inside of there first. And I see we do have a couple power rules. Remember, power rule as we're condensing, kind of follow this order. So let's go ahead and bring those in. That's going to give me the natural log of y squared plus the natural log of 2 cubed, which I'll go ahead and evaluate to 8. 2 cubed is 8. Okay, now inside of here I see we do have 2 logs being added, and that is the product rule, right? If they're being added, we can multiply them together. So this gives me the natural log of 8y squared. Y squared times 8, we'll just usually put the 8 in front. And now these outer parentheses are really unnecessary because there's only one term in there now. but we are subtracting these two logs. And that is our final one, the quotient rule, which says I can write it as 2 logs with a single fraction in the order of the top over the bottom. And I didn't mention in some of the previous ones, but if you do get a fraction that reduces, like here, or even with variables, you want to go ahead and reduce those. In this case, nothing reduces here. Sure, there would be some restrictions on our variables, of course, like they can't be negative, and our denominator can't be 0, etc. But don't read too into that yet. Okay, so here's some examples. What if I want to go backwards? Instead of condensing, what if I want to expand? Well, then I'd want to do these rules backwards, essentially, right? I'd want to go this way and follow the order of operations backwards, which means I actually want to look for things that have to do with the quotient rule first. Are there any logs, or is there any division in my logs? Remember, I'm trying to expand, so we're trying to go that way. I don't see any fractions, so we can skip the quotient rule. Product rule is next. Do I have any logs with multiplication? Anything's held with multiplication that I can separate into 2 logs being added? Yep. 25 times x cubed can be written as the natural log of 25 plus the natural log of x cubed. We can separate those with addition. Now, could you separate 25 as 5 times 5 and write those as 2 individual logs? Yes. There's another way we can also handle that we'll try here. You could even think of 25 as being 5 squared. Right? It happens to be a perfect square. And then we can use the power rule on both of these. So if we did that, we brought our 2 out here and our 3 out here. Remember, this time we're taking the exponent out, right? Because we're trying to expand and get to that form. So we're going to bring them out as multipliers. We get 2 times the natural log of 5 plus 3 times the natural log of x. And that big, long, expanded answer is what we're looking for. Now, let's say instead in 25, if you had split that up as the natural log of 5 plus the natural log of 5, if you had gone that other route, well, that's the same thing added twice. Isn't that the same as 2 natural log of 5s? Yeah, right. So we can combine those even though we're expanding, right? We still want to combine like terms, and technically we would have 2 natural logs of 5. Okay, let's try our next one, example 5. First, look for quotient rule, and we absolutely have division. Let's separate them as 2 logs being subtracted. So the natural log of the top, x squared y cubed, minus the natural log of the bottom, which is the number e. Next is the product rule, and we do have some things held with multiplication, and we can separate those as 2 logs being added together, minus the natural log of e. And then we have some power rule. Right, lastly, our power rule. We do have some exponents to bring out. So we get 2 times the natural log of x plus 3 times the natural log of y minus the natural log of e. Now, natural log of e is actually log base e of e. Log base e of e. Which is really, if I wanted to know its value, remember this is saying e to what power is e? We actually even learned a property that said log base b of b was always 1. And in fact, that is true here. The natural log of e really has a value of 1. You can try that in your scientific calculator. It should have a natural log key on there and an e key. The natural log of e is exactly 1. So in fact, even though we're expanding, we could simplify that value. And this is the expanded final answer. I would highly doubt anybody would leave natural log of e not simplified to -1 there. Okay, here's another one. We need to be a little more careful when there's multiple things in the bottom we're going to separate, but we'll try this one out. So quotient rule, 7x squared minus log of 2y. Power rule, product rule. We're going to separate things held with multiplication as logs being added. Log of x squared minus, now I'm going to separate these, but it's minus this whole log. And when I expand this into two logarithms, I need to make sure it's subtracting all of that. So we need a grouping symbol. So I'm going to use brackets here. Log of 2 plus log of y. Now, if you want to get rid of the brackets, you can distribute the negative sign in and just make them both negative. That's fine. I'm going to go ahead and use the power rule. It looks like just one exponent to come out. And maybe we'll go ahead and expand the negative sign to both of those at the right. So 2 times log of x. We'll kind of distribute the negative sign here to make negative log of 2, or minus log of 2, and minus log of y. And kind of a general rule, if we were going to go back and condense this, kind of a general rule, positive logarithms always end up in the top of our quotient rule. Negative logarithms always end up in the bottom. That also has to do with, like, if you bring it in as an exponent, a negative exponent would move you into the denominator. I don't know if that's more confusing or not, but let's move on. Okay, so these ones, this last part here, these are kind of like fun little puzzles in this section to really see if we understand these and to challenge us a little bit. So using these two pieces of information here, log base 5 of 3 is about 6.8, and you can check that with the calculator and change a base formula. And log base 5 is about 1.21. Using those two pieces of information, approximate each of these to 2 decimal places without a calculator. So we're going to be able to use our rules here. And I know the numbers I can kind of work with are 3 and 7 in base 5. So I'm looking at the number 21, and 3, and that's 3 times 7. So what if I rewrote 21 as 3 times 7? Well, if we have things multiplied, we can expand them out with our properties of logs. There's 2 logs being added together. Log base 5 of 7. And if we're adding these 2 logarithms, well, what is log base 5 of 3 equal to? About 0.68. What is log base 5 of 7 equal to? About 1.61. Sorry, 1.21. And if you add those together, go ahead and line up my decimal places there, we get about 1.89. This logarithm, without going to a calculator, just knowing these 2 other logs, I can find its value. And this is what you had to do back in the day when there were just log tables and calculators couldn't do this for you. You had to kind of work these puzzles on your own. So it's good mental exercise here. Well, what do you think we need to do here? If I've got division, we can separate them as 2 individual logs with subtraction via our quotient rule. So log base 5 of 7. So log base 5 of 3, that's 0.68 for this one. Log base 5 of 7, they said is 1.21. Now notice we are subtracting more than we have, so we are going to get a negative result. But when you are subtracting by hand, you do line up your decimals. You always put the larger number on top. Just remember that your answer will be negative here. So, we're doing a lot of borrowing. That becomes 12, but I got to borrow from that, so that's 11. And this becomes 11. And, well, what do we get here? 11 minus 8 is 3. Okay, we borrowed from there, so 6 from 11. Yeah, I don't know why I wrote my numbers in that order. 8 from 11 is 3. Well, we can't take 6 from 1, so we borrow from here. 6 from 11 is 5.53. So negative 0.53. Again, just remember when you're taking away more than you have, your answer is negative, but when you're subtracting by hand, you always put the larger digit on top. Okay, number 9. 49. I don't think I can do anything with 3, but that is, I could think of that as 7 plus log base 5 of 7, right? 7 times 7, so we could separate them there, right, using our product rule. Or, what if I thought of that as log base 5 of 7 squared? Then I could bring that exponent out and do 2 times log base 5 of 7. Either one of these will give me the correct answer, by the way. Right? This is just 2 log base 5s of 7s. 2 log base 5 of 7s. So the same exact idea. So if we do 2 times log base 5 of 7, which is 1.21, that's a pretty easy number to double by hand. We get 2.42. Okay, or you can add it to itself twice. You get the same result, of course. So here's a couple more challenging ones for you here. I would say go ahead and try these out. You can pause the video. I'll put them at the end. But give these last 2 a try. They should challenge you quite a bit. We haven't really gone over a trick that will help you. We sort of did when we talked about log base E of E or log base B of B. That might be a good hint. But try these 2 out and then unpause in a second. All right, here's our final answers. And the trick ended up being here. You had a secret number that you could use that they didn't tell you. Log base 5 of 5 is 1, because remember 5 to the first power is 5. Now in fact, any power of 5 like 25, right? Log base 5 of 25 also has an answer you could use without a calculator, because 5 to what power is 25? 2. This whole logarithm just has a value of 2. So, in fact, any power of 5 you can use in base 5, including fractions like log base 5 of 1/5, right, is -1. 5 to the negative first power. We'll put that in the bottom. Anyway, so that was kind of the secret there. Log base 5 of 5 you could use. That definitely helped you with number 10. And number 11, just breaking them down, is 9 and 7, and 9 is 3 squared. Helped you finish. Okay, that's it. We'll definitely run through a bunch of examples in class. Thanks for listening.